Pabili po.
So what I'll be talking about is a brief introduction of a probability distribution function. But before we tackle this, we need to first understand what a probability distribution. So a probability distribution is a list of all of the possible outcomes of a random variable along with their corresponding probability value. So now you wonder what a random variable means. So a random variable is a variable whose value is the outcome of a random event. For example, a random variable could be the outcome of the roll of a die or a flip of a coin. So there are two types of a random variable. One is continuous and the other is discrete. So a discrete random variable can take on a distinct or separated values or unconnected value, while for continuous random variable, it can take on any value in a range, and that range could even be infinite. I'll be going to give some few examples. So for a discrete random variable, the number of people in a church. So there are no fractional parts of a person, and this same goes with the number of chairs inside a classroom and the number of books in a bookshelf. Now for a continuous random variable, an example is the exact amount of a random animal in a zoo. The mass of a random animal or any object in our universe, it can take on a whole set of values, and you can have a random animal with a mass of 123.45678 kilograms and so on, and you can have an infinite value. Another example, the time to complete reading a book. This could be measured in fraction of seconds. So now for probability distribution function, let's ask first what a function is. On an abstract level, a function is a box that takes on an input and returns an output. Let's say that this function takes in a number as input, adds 2 to the input number, and returns to the new number as output. So graphically, our function as a box looks like this. So if our input was 5, our function would add 2 to it and return the output 5 plus 2 equals 7. Now let's use symbols instead. We change the word input into x, the word function into f, and the word output into f of x. The diagram can now be written as this. So now for the probability distribution function, the probability distribution as a concept can occur in two ways. It can be a probability mass function or a probability density function. So a probability mass function, or commonly abbreviated as PMF, takes on discrete random variable, while a probability density function, or PDF, takes on continuous random variable. Let's talk about first the PMF. So a probability mass function, which we'll call f, returns the probability of an outcome. Therefore, a probability mass function is written as like this. Now let's go to probability density functions. PDF are slightly more complicated conceptually than PMF. Let's look on an example first. This is an example of a continuous probability distribution. You can see that the numbers on the vertical axis start at 0 and go up. This is a rule that a PDF has to obey. Any output value from a PDF is greater than or equal to 0. In mathematical lingo, we would say that the output is non-negative, or write this mathematically as, to get the probability from a PDF, we need to find the area under the curve. So from this example, we can find the probability that the outcome is between 0 and 1 by finding the area shown in the image. So mathematically, we would write this as, we can read this as the integral of the probability density function between 0 and 1 is equal to the probability that the outcome of the random variable is between 0 and 1. So now we've seen another property of PDF, namely that the probability between two outcomes, let's say A and B, is the integral of the probability density function between those 2 points. So mathematically, this is. So now we've finished the video, and I hope that you've learned something from this. Thank you.
We are here to present about the Weibull distribution. So first, let me give you a brief history about the Weibull distribution. The Weibull distribution is named after its originator, the Swedish physicist Walody Weibull, who in 1939 used it to model the distribution of the breaking strength of the materials. Since then, the distribution is widely used. It was Weibull suggested a scale parameter and a location parameter that made the distribution meaningful and useful. I will discuss about the Weibull shape parameter, or beta. The Weibull shape parameter, also known as the Weibull slope, this is known as the Weibull slope because it is said that the value of beta is equals to the slope of the line with the probability plot. Now, the different values of the shape parameter can have marked effects on the behavior of the distribution. In fact, some values of the shape parameter will cause the distribution equations to reduce to those of other distributions. Now, for example, please refer to the picture in the PDF. Now, as you can see in the figure, it shows the effects of different values to the shape of the parameter. You can see the shape can take on a variety of forms based on the value of beta, or the shape parameter. Next is the Weibull scale parameter, also designated as eta. It is a change in the scale parameter, has the same effect on the distribution as the change of the abscissa scale. Now, the abscissa scale is the distance of a point from the y-axis on the graph in the Cartesian coordinate plane. Now, it is said that if eta is increased while beta and gamma are kept the same, the distribution gets stretched out to the right and its height decreases while maintaining its shape and location. This also can be used vice versa. When the eta decreases, the distribution gets pushed to the left. You can see in the graph provided, and also eta has the same unit as t, or time. Lastly is the location parameter, which is designated as gamma. Locates the distribution along the abscissa. Changing the value of gamma has the effect of sliding the distribution and its associated function either to the right if the gamma is greater than 0, or to the left gamma is less than to 0. These are the characteristics for the location parameter. When gamma is equals to 0, the distribution starts at time equals to 0, or at the origin. If gamma is greater than 0, the distribution starts at the location gamma to the right of the origin. And if gamma is less than 0, the distribution starts at the location to the left of the origin. Gamma provides an estimate of the earliest time to failure of the units under test. Gamma must be less than or equal to the first time to failure. The life period of 0 to plus gamma is a failure-free operating period, meaning no failure must occur during this period. Now, gamma may assume all values and provide an estimate of the earliest time at which a failure may be observed. A negative gamma may indicate that failure have occurred prior to the beginning of data collection period of the analysis, meaning if you have a negative gamma, some or majority of the failure happened before you gathered the data for the analysis. For example, failures might have occurred during production, in storage, in transit, or during checkout prior to the start of the mission or prior to actual use. So we can know if failure happened during these examples, happened before we collected the data, if we have a negative gamma. And that's it for my report. Thank you.
The two-parameter Weibull is the simpler version of the Weibull distribution. This distribution is defined by two parameters. And also, two-parameter Weibull is often used in failure analysis because no failure can happen before time 0. The cumulative failure distribution function f of t is equal to 1 minus exp minus the quantity of negative t over n raised to beta. This is equation 3.9, where t is equal to time and the beta is equal to the Weibull slope. So the Weibull slope is the slope of the failure line on the Weibull chart. It is also referred as the shape parameter. So n is the characteristic life, or the time by which 63.2% of the product population will fail. It is also referred to as the scale parameter. So equation 3.9 can be rewritten as 1 over 1 minus f of t is equal to the exponent of t over n raised to beta. This is equation 3.10. Or by taking two natural logarithms in equation 3.10, it will take the form of two natural logarithm 1 over 1 minus f of t is equal to beta natural logarithm t minus beta natural logarithm n. This is equation 3.11. It can be noticed that equation 3.11 has a linear form of y is equal to beta x plus c, where x is the natural logarithm t, y is the 2 natural logarithm 1 over 1 minus f of t, and c is equal to the negative beta logarithm n. So this is equation 3.12. Therefore, equation 3.11 represents a straight line with a slope of beta and intercept c on the Cartesian xy coordinates 3.12. If the data follows the two-parameter Weibull distribution, the plot of natural logarithm 1 over 1 minus f of t against the natural logarithm t will be a straight line with the slope of beta. That is all about the two-parameter Weibull, and I hope you learned from this video. Thank you.
Hello everyone, so we will now be discussing about the 3-parameter Weibull distribution, which is, I'm sure, the 2-parameter Weibull distribution had been discussed to you already. And this will be just an extension of it. We will be just having an additional parameter, which is the location parameter. In reliability engineering, Weibull probability analysis distribution is probably the most widely utilized way or technique of processing and interpreting live data, and it is mainly because of its flexibility and easy interpretation of the distribution parameters and their relation to the failure rates and bathtub curves. So now we have here the formula of a 3-parameter Weibull. So where in the product cumulative failure distribution function is equal to 1 minus the exponential of the negative quotient of time minus gamma over the scale parameter raised to beta. So based from this formula, and like what I have said, 3-parameter Weibull distribution is just an expansion or extended version of the 2-parameter Weibull, because we will be introducing an additional parameter, which is the gamma parameter, or what we call the location parameter. So under the assumption of a 3-parameter Weibull, no failure of the product can possibly occur prior to the time. That's why we can also call this added parameter as minimum life. So we have a sample graph here of a 3-parameter Weibull distribution. And as you can see, unlike the 2-parameter Weibull distribution, a 3-parameter Weibull distribution can no longer be represented by straight line. So from this graph, the shifting of the gamma determines its maximum life. Now, for a positive location parameter, it indicates that the particular distribution is always 100%, while if the location parameter is negative, it only implies that the failure occurs before time 0. So the relationship of beta parameter to failure rates and bathtub curve, we have here a graph. So the value for beta reflects the hazard function or the expected failure rate of the Weibull distribution, and its value can either be less than 1, equal to 1, or greater than 1. If the value for beta is less than 1, it indicates a decreasing failure rate and is usually associated with infant mortality. And if the value for B is equal to 1, a constant failure rate and is usually associated with useful life. While if the value for beta is greater than 1, it indicates an increasing failure rate and is usually associated with wear out corresponding to the end life of the product. So that's it for the 3 Weibull parameter. I hope you have learned something and stay safe.
Hi, I'm Rachis Arya, and I'm here to discuss the relationship of beta parameters to failure rates and the bathtub curve. Now, the beta parameter, as we all know it, is also known as the shape parameter, the Weibull slope. This simply represents the failure rates in a bathtub curve. Now, the bathtub curve is a representation of a product's lifespan. It is visualized as the failure rate of a product per unit time. Bathtub curve simply starts with a downward slope, then transitioning into a straight slope, transitioning into an upward slope. Now, the downward slope, that is also called the burn-in period, or biologically the infant mortality or the early failures. The most stable part of the bathtub curve is its prime time, or the useful life, where the product is simply expected to work with very minimal failures. Nearing the end of the lifespan of the product, we have the wear out period, where a lot of failure is expected to happen due to age of this product. Now, in the downward slope of the bathtub curve, this is the burnout period, where there is a lot of failure expected also to happen here, but it's in declining manner. The Weibull distribution, its beta value should be less than 1 due to the decrease in failure rates. that the less than 1 value simply represents the slope of this section of the bathtub curve. These type of slope in the bathtub curve are simply automatically associated with the infant mortality section of the bathtub curve. Now when it comes to the most stable part of the bathtub curve, the useful life, the slope or the beta parameter of the Weibull is simply equal to 1 or about 1. It's a constant failure rate and is usually associated with useful life. In the useful life section of the bathtub curve, constant failure rates are somewhat expected to happen here. In the rightmost section of the bathtub curve is the wear out. When a product is nearing its end, this is where an increase in failure rate happens. Now when that increase of failure rate happens, the slope tends to go higher than 1, or the beta parameter is greater than 1. Now, in the whole lifespan of the product represented by the bathtub curve, you can see that the Weibull distribution simply shows the failure distribution of the lifespan of the product with the beta parameters. Now, there are cases when the Weibull slope tend to go into extremes. Sometimes these slopes can go up to greater than 6. When it comes to this, you should become slightly suspicious. Although 6 might be a large number for a beta parameter, some say that high beta values implies low variability. If tests have high value betas, it simply can indicate that a failure can happen into a small time span.
Hi, this is Renzo Bombay, and for my topic, I'm going to discuss the mean, median, and mode of Weibull distribution. I have here an example of group data which we will get the mean, median, and mode of this table. But first, what is mean, median, and mode? Mean is the average value of the data. Median is the middle value. Mode is the value that appears most often. I already took the liberty of solving and inputting all the values, but I will show you how it was done. The first two columns, which is class and frequency, is given. Frequency is the number of times which the event occurred. For the third column, we have the midpoint, fourth is the FM, and the last is the CF. To get the midpoint, you add the lower limit and upper limit and then divide it by 2. So here you add 150 and 154 divided by 2, that is 152. Repeat that until you get to the end. For the fourth column, which is FM, just simply have to multiply the F and M. For the CF, which is cumulative frequency, to do it, you copy the first frequency, which is 2, and then add the second frequency, which is 5, you get 7. So continue doing that until you reach the end. For the mean, which is x bar, the formula is x bar is equals to summation of Fm over summation of F. Let's solve. So x bar is equals to 7,228 over 44. You'll get 165.636 or 165.64. We already have the mean. For the median, m is equals to L plus open parenthesis 1/2 times n minus f all over Fn close parenthesis c. L is the lower boundary, n is the total number frequency, f is the cumulative frequency above the median class, and fm is the frequency of the median class, c is the class interval. To get the median class, just divide the total number of frequencies into 2. So 44 divided by 2 is 22. Now what does 22 means? We'll get this 22 and compare it to the cumulative frequency. You get the value which is immediate higher than 22. 32 is higher than 22 and it is the immediate higher value. This will be our median class. This encircled row. Now to get the lower boundary, just subtract 0.5 to the lower limit. 165 is our lower limit. Minus 0.5, that is 164.5. For the n, that is the total number of frequency, and f is the number of cumulative frequency above the median class. So this is our median class. Above that, the cumulative frequency is 18. And for the FM, it is the frequency of the median class, which is 14. And for the class interval, you have to subtract from upper boundary, the lower boundary. So just subtract 0.5 and add 0.5 to the lower limit and upper limit. The answer is 5. So that is our class interval. So input all those data in our formula. 164.5 plus 1/2 times 44 minus 18 over 14 times 5. You'll get 165.92 or 165.93. That's our median. Now lastly, we have the mode. Mode is equals to L plus F1 minus F0 all over 2 times F1 minus F0 minus F2 times C. But we will also get the modal class. The modal class is just the value that has the highest frequency. And here in our table, the highest frequency is 14. The modal class is the same as the median class. This is also the row of our modal class. So for the F1, that is the frequency of the modal class. F0 is the frequency before the modal class. And F2 is the frequency after the modal class. And C, again, is class interval. So for F1, our frequency for the modal class, 14. F0, which is 11. And for F2 is 9. So we have all the values for the formula. Input that in your solution, 164.5 plus, open parenthesis, 14 minus 11 over 2 times 14 minus 11 minus 9 times 5. You'll get 166.375 or 166.38. So, there you have it. We have the median, mean, and mode. So, thanks for listening. Again, this is Ren sa Bombay.
Hi, I am King Philip A. Sagon and this is my assignment for our subject, which is reliability engineering. So beforehand, I have searched videos upon this assignment, this topic. It is also in YouTube. It is Quarantine Boys from the channel. Let's proceed. First is probability distribution. So what is it? It is a list of the possible outcomes of a certain object. So under this, it is also mentioned that it has two random variables, which is discrete and continuous. Proceeding to it, probability distribution function is broken down into two subtopics. It is probability mass function and probability density function. So discrete and continuous random variable is used for the aforementioned respectively. Proceeding is the Weibull distribution parameter. It is composed of three main characteristics. First is shape, then scale, then location. Besides from the said characteristics, the Weibull distribution can also be in a form of two or three parameters. The two-parameter model is a simpler version of a Weibull distribution. And on the other hand, the three-parameter is used for utilizing to interpret life data. Proceeding to the next topic, we have relationship between the bathtub curve and the Weibull slope. As for the bathtub curve, it has three phases. First is the infant mortality of an early life failure. It is the beginning of a certain kind of event. Hence, failures are decreasing. So the next phase will be the useful life or the life in between failures. This is a kind of failure wherein the failure rate is constant. So the next would be the last phase, which is the wear out phase. In this phase, the product is said to have a high failure rate. So lastly, I will be discussing about the mean, median, and mode. So for the mean, it is the average value of the said data. Second is the median, which is the middle value of the data. And then mode will be the value that appears most often. So now I will be showing you the equations used for each. Here is for the mean, here is for the median, and this is for the mode. So that is my assignment for this subject, reliability engineering.